Knowing the definitions of the constants that define our base units, we can now take a look at the base quantities, and whether or not that's the correct terminology, it'll do. And we'll turn those base quantities and associate them with our base units momentarily. I took some time to try and color code this. We'll see how it goes. The first one we had looked at was the second, and the second was based on the cesium-133 isotope, its frequency of excitation. So we're going to put that as the first one there, and that is time. I'll just label these right here. These are our quantity and the associated unit. I'll need more space for some of these than others. All right, so time, we've got a unit of the second. We'll work our way around clockwise. Kilogram is a measure of mass. And just as a quick side note, very often in class, kids will ask why the kilogram and not the plain old gram. And I think a simple reason is because grams are pretty small. If you remember what I had mentioned about the definition of the kilogram, it was originally based on a metal cylinder in a jar in France. So a gram would have been a really small metal cylinder. That's my guess on how and why that happened. And we had said that the kilogram is currently based on Planck's constant. I neglected to mention this detail earlier, so I had to go back and record it. So hello from the future. I want to go back and take a little look at mass, which we said was measured in kilograms. If you think back even further, we had talked about pounds versus mass and things like that. So let's take a moment to discuss that. And we're going to talk about the distinction between mass and weight. And the good news is the numbers are pretty much the same at sea level on the Earth. All right. So there's a lot of pedantic back and forth with people about, oh, that's mass, or when you use a balance, that's massing, not weighing. That's all true. But on the Earth, the numbers for those two units are pretty much interchangeable. So don't get too upset. So mass we've already defined as a measure of the amount of matter. In a sample, so a measure of the amount of matter in a sample. And so what is then weight if it's something else? And weight is a measure of the effect of gravity on a sample. So instead of looking at an amount of matter, we're looking at a force. And so like the discussion that we need to have, just so we feel like we've been thorough, is what do we use to measure these things, and what changes and what doesn't as we move around in the world and in the universe. So mass, how much matter you have, no matter where you are in the universe, the amount of stuff that makes you up doesn't change. So this doesn't change based on location. Right? The amount of stuff that makes you up does not change, so mass doesn't change based on location. However, the effect of gravity does change based on location. If you look at, well, I'll write it down in a second here, but the law of gravitation, distance between these objects and the mass of the objects determine the force of gravity. So this does change based on location. So a common example is that if you went to the moon, your mass would not change because the amount of stuff does not change. But if you go to the moon, your weight would change because the gravity is lower. And feel free to tune out as I write this, but it's an inverse square law, that relationship. And the force of gravity is some constant times the mass of the first object, mass of the second object, over the distance between them squared. So your mass isn't going to change as you go from place to place, but the moon has less mass, so that force of attraction is going to decrease. All right. So weight, we're talking about a force, and mass, we're talking about an amount of matter. So what do we use to measure a mass? We measure it using a balance. And again, if you want to be super pedantic, which I don't encourage, you could use the right terminology, which is to get a mass, you are massing something, right? And you might use, I happen to have one right here, something like this dialogram balance. And what you are doing is comparing standards of known mass, things with a known amount of matter, to an unknown sample. All right? So you've seen it like, interestingly enough, the scales of justice or whatever. That is a type of balance. You're comparing a known amount of matter to a sample with an unknown amount of matter. And I feel like it would probably be good at this point to write those words. You are comparing a known amount of matter to a sample with an unknown amount of matter. Sorry, I was checking my lines there. Now that that's completely garbled and impossible to see. So how do you measure the weight of something? Well, you've done it. You go into your bathroom, perhaps, and you hop on a scale. So that is the instrument you use for that. All right. That's why I was laughing about the scales of justice actually being a balance. But anyway, how does a scale work? It measures force, right? So a typical old scale would be a spring scale where you step on it and it compresses a spring. And you may or may not know or care, but those springs follow F equals kx. It's a linear relationship. I know you don't care. So anyway, so a scale measures force. And you may recall we had said that there is such a thing as pounds mass, or you can use kilograms or something like that, and of the effect of gravity. And you can use something there. Just checking if you can see this. You can use something there, pounds force, or you can use newtons or something like that. So it's worth noting that this is the situation where we see pounds mass and pounds force, which happen to be numerically equivalent more or less on the surface of the Earth. So that's why you see that interchange. We'll get back to our other units right now. Moving right along here, the mole is the SI unit for the amount of a substance. And this is very often a topic that confuses people, but I think that it's a matter of people overthinking. So what is the mole? I'll cover that up and I'll ask a different question, which is what is a dozen? All right, a dozen's 12. Of what? Of whatever you have 12 of, right? So what is a pair? A pair is two. Two of what? Of whatever you have, right? You may know a gross, which is a dozen. What's a gross? 144. Of what? Of whatever you have. What's a mole? A mole is 6.022 times 10 to the 23rd. Of what? Of whatever you have, all right? It's a big number. And the reason it's a big number is because atoms are really tiny. And that's a true story. I'm not just making that up. So this is 6.022 with some other numbers, times 10 to the 23rd of something. Right? 6.022 times 10 to the 23rd. If it were 6, you'd have no problem. Oh, a mole is 6 of something, right? Just like a dozen's 12. Well, it just happens to be a much bigger number, and we have to use scientific notation. So 6.022 times 10 to the 23rd donuts, which would cover the surface of the Earth. who knows how deep. And again, historically, it was based on the number of particles in a certain mass of carbon, a specific isotope of carbon. But now it's just based on that constant, right? This number here is what we call Avogadro's number, capital N, subscript capital A. All right, enough words there. The candela is luminous intensity. And again, historical origin based on how bright a candle is. That's a lowercase c and a lowercase d. Sorry, it doesn't look like that. I've also seen this as luminous efficacy or something, I can't remember, but luminous intensity is how that's commonly seen. We've got Kelvin, and this one's rather important. So temperature, that's in Kelvin, named after Sir Lord Kelvin or whatever. And it's good for us to sneak in a definition right here. Definition of temperature, in fact. And this is, I think, a neat one to define in class because a lot of people don't know how to define temperature, right? So what is temperature? A lot of people will say how hot or how cold something is. In fact, I recently saw a definition from somebody's college notes that said a measure of hotness or coldness of a substance, which is really weird, all right? The technical definition of temperature is a measure of the average kinetic energy of a sample, all right? So a measure of the average kinetic energy of a sample. All right, and kinetic energy, you may or may not recall from like a first year intro to physics class or whatever. Very often you'll learn that kinetic energy is the energy of motion. And all of the particles are moving. Some are moving faster and some are moving slower, and then it is the average, all right? But none of them are moving at zero at any temperature except, and some of you may know this term, absolute zero. Right? And that is 0 Kelvin. And that's not okay. I put a 0 as a null set, essentially, a 0 with a line through it. Otherwise, people think I wrote okay. But absolute 0 is 0 Kelvin, where there's a total absence of heat. If you hear clinking in the background, that's my dog going up and down the stairs. He wants to go hang out in the rest of the house. I'm in the basement, but he can't be trusted unsupervised, not unlike my children. Anyway, absolute 0, neat vocabulary term. And a lot of people will say, you know, what about Fahrenheit and what about Celsius and other things like that? And the short answer is those aren't good enough. In fact, as I say to my students, those are never good enough. And there's a simple reason for it, which is when you have Fahrenheit or Celsius and things start to get colder, 32 Fahrenheit is where water freezes, that's 0 Celsius. And what happens if things get colder than that? Well, then all of a sudden you get into negative numbers. And if this is the energy of motion, how can you have negative motion? And I think it's an interesting discussion, all right? So let's write out that equation for kinetic energy. Kinetic energy is 1/2 mv squared. And by the way, it's kind of neat to look at the units that are there. This m is mass, which is in kilograms. And you can't have a negative mass. It has to be positive, right? And v is velocity, which is going to be in meters per second, and we're going to end up squaring that. So it could be positive or it could be negative. It doesn't matter because when we square it, it will end up positive. So kinetic energy always has to end up positive. So can we have a negative temperature? No, because we can't have a negative kinetic energy. And I did skim something. Tune out if you don't like information. But you can have a negative velocity, and if you remember from a previous video, velocity is a vector quantity. It has magnitude and direction. So moving in one direction would be a positive velocity. Moving in the opposite direction would be a negative velocity. So you could have a negative velocity, but we're squaring it, so it ends up positive. And then kinetic energy has to be positive. So negative Fahrenheit, negative Celsius don't make any sense fundamentally. Now, where do they come from? Celsius is super slick. You can come up with your own Celsius thermometer. You put it in some freezing water, that's 0 degrees Celsius, and you put it in some boiling water, and that's 100 degrees Celsius at atmospheric pressure. And then you have a thermometer. You just draw the marks in between. And interestingly enough, the increment size on a Kelvin thermometer is the same as the increment size on a Celsius thermometer. So the distance between the marks, it's just different numbers. And what's so slick about the Kelvin scale is it starts at 0. All right, it is what we call an absolute scale, an absolute thermodynamic scale. It starts at 0. All right, so I know that was a lot of words about temperature, but the short of it is Fahrenheit and Celsius, never good enough. Kelvin starts at 0. That's awesome. All right, and those Kelvin increment sizes, the distance between the lines on the Kelvin thermometer, are the same as the distance between the lines on the Celsius thermometer. And I guess P.S. you have degrees Fahrenheit and you have degrees Celsius, but Kelvin does not have degrees because it's an absolute scale. All right. So Fahrenheit and Celsius, you have degrees. Kelvin, you don't, because it's an absolute scale. And that may be something else that you haven't heard of before, which is kind of slick. Number 6 here is our electric current. And I mentioned earlier that if you go to the breaker box in your house, you'll see current ratings like 15 amps or whatever. Pretty much any electronic device you have, you can see some current rating on, and I know there's a 0% chance you can see this, but it's just a brick, a charging brick or whatever. And if you look at this one in particular, it says output 5 volts at 1.0 amps. All right, so take a look at some of your electronic devices. This is the AC adapter for the laptop, and I'm guessing you can't see that super well either. And then if you look somewhere, it's going to say input and output. This one outputs 2.25 amps at 20 volts, or 3 amps at 15 volts, or 2 amps at 5 volts. So amperes, just the number of electrons passing a point in a certain amount of time. And that, we had said, is measured in amperes for electric current. And that leaves our last one here, which is distance, or length. Which we said we're going to measure in meters. And believe it or not, upper and lower case do matter. In general, the scheme is if you have a unit that's based on someone's name, like Kelvin, it'll be capital. But then if you have something that's not, you have lowercase. So we have lowercase kilo, right, grams, mole, lowercase. This should be a lowercase c. It's just drawn very poorly. Capital A, ampere, and lowercase m, meter for distance. And we had said this is based on the speed of light. Now, those base units are things that we can use to come up with anything else we need. So, for instance, I mentioned velocity over here, and I wrote meters over seconds. So what I want to look at in the next video is the SI derived units, which are combinations of these base units.